pretty close to where, yeah, we can see it. So we're going to be looking at the bomb calorimeter. And this is a way of measuring the change in enthalpy. For a chemical reaction. Right, now with our bomb, it doesn't actually explode if we've done our chemical reaction correctly, but it's called a bomb because it looks a bit like a bomb. And what we've got then is an insulated container. And we've got an insulated lid as well. And we do need a thermometer, because we need to be able to measure the change in temperature. That's what we're interested in finding out. We also have a mixer that is going to be able to make sure that we are measuring the temperature for the entire reaction's change in temperature. Okay, so this is our reactants. Okay, and what we are interested in finding out is our initial and final temperatures. Now, what we do with a bomb calorimeter is we calibrate it. So the calculations involving the bomb calorimeter always have two steps to them. So step one, calibration. And that is where we add a known quantity of energy. We add it to a known quantity of water. And we're measuring that change in temperature. Okay, and so what we've got there fixed is the energy we're adding, the time, and the quantity or the mass of water. So when we're talking water here, we're going to be considering its mass, and we do know that the density of mass, of water, the density, which is mass on volume, is 1. So 1 gram of water has a volume of 1 mil. Okay, and so we've got our little formula for calibrating the calorimeter, that V I T equals H. And here remember that H is our enthalpy, V is the volts, I is the current, T is the time.
So it's represented as an E on our formula sheet. Does it matter which one we use?
No. So instead of H, yeah. No, it doesn't matter. It can be E or H. And the reason why is they're both measured in joules. And then what we need to do then is to find out the calibration factor. So we want to measure the energy in, and then the calibration factor will be that divided by the change in temperature. All right, so on page 21, you've got a picture of the kind of calorimeter that we use here, and you're going to do this prac. You've got terminals at the top. Oh, okay, I should put terminals here. We use the terminals only during the calibration phase. Okay, so we're zapping the water, and then we want to measure the change in temperature of the water. And then what we know is, we know how much energy we've put in, and we know how much the temperature has changed for the water. And so when we then next do a chemical reaction in that calorimeter, and we see the temperature change, then we can work out the energy of the reaction. Okay, so that's why we only, and this happens so often, is that students will calibrate it and then they try and hook it up again for the reaction. You don't need to hook it up for the reaction. What you're going to do is then just measure the change in temperature from the reaction. Now, yes, it's not a perfect, it won't be perfect, you won't get perfect results, because what we're assuming is that all of the energy from the reaction is going into increasing or decreasing the temperature of the water. But there will be losses. In what way do you think we might have losses? Where can we have losses?
Is it because it's not completely filled with water? There's also gas inside? Or?
Well, no, it's more about the fact that we're assuming that this insulation is perfect, aren't we? Because, and it can't be. So there will be some losses. So we would always expect that our measurements would be less than the ideal result, because we would assume that we've lost some, if it's an exothermic reaction, that not all of that energy has remained in the water. We use water. Water's great because water has a very high heat capacity. Did I talk about that in a video? Yeah, so that's why we use water to cool combustion engines in our cars, etc. It's great at that. We also use heavy water to keep nuclear reactors cool. So water has very good heat capacity. So it takes a lot of energy to increase the temperature of water by 1 degree. All right, so let's plug in some numbers with our example for the bomb calorimeter. And this is on page 22. Okay, it tells us that a bomb calorimeter is calibrated, so we know that's step 1. We've got 2 amps. What symbol represents amps? I. And we have the time. It's on for 210 seconds, and the potential difference was 5 volts.
410 seconds.
The temperature rises by, so delta T is 0.820 degrees C. Calculate the calibration factor. So firstly, it's to calculate the energy, where VIT is equal to E or H, whichever letter you wish to use. So it's going to be 5 times 2 times 210, and we get 4,100 joules. Now, again, it's the joules and the kilojoules that get people tangled up a bit. So,
Should that be 410 instead of 210?
oh, yeah, it should. The SI unit for energy is joules, but we calculate mostly in kilojoules. So what we might do here is, because our calibration factor or our specific heat capacity or our energy is often quoted in kilojoules, is we'll convert it straight to kilojoules. And now the calibration factor involves this change of temperature that occurred during the calibration phase. So we're going to divide the energy. So this is equal to delta H on delta T is 4.1 divided by 0.820 gives us 5 kilojoules per Celsius, per degree Celsius, or it could also be expressed as 5 kilojoules per Kelvin. It doesn't really matter because they're the same increment size. So that was our calibration. Now we have our experiment that we're doing in our bomb calorimeter. Now it tells us that we have 0.5030 grams of hydrazine, rocket fuel, and it's burnt in the calorimeter, and T1 was 24.62 and T2 was, and that's in Celsius, 28.16. Then we want to know the molar heat of hydrazine. So, the heat of this reaction so that's just the reaction that we're doing in the calorimeter. We're going to multiply the calibration factor by this change in temperature. Not this one up here, but this one down here. And so it doesn't look like we've, apparently it's 3.5 degrees. So we're going to multiply our calibration factor by the change in temperature of our reaction, and we get 17.7 kilojoules. But that is not the answer to the question, because that's only for 0.5030 grams of hydrazine. Now we need to know, well, how many moles do we have here? So our moles are going to equal our sample mass divided by the molar mass of hydrazine, which according to the booklet is 32, but what have we got? 2 times 14.01 plus 4 times 1.008. Let's just assume that's right. 0.01572 moles. So then that was the energy released from this many moles of hydrazine. Now we want to figure out, well, how many kilojoules of energy will be released from 1 mole of hydrazine. So what we need to do is divide our answer by n to find our molar mass. So 17.7 divided by 0.01572, 1130 kilojoules per mole. Okay, so where do people go wrong? People go wrong getting confused with the two temperatures. And people go wrong here when getting a bit confused about joules and kilojoules. But the most important thing to remember when trying to solve this is that it is going to involve two separate sets of calculations. First one to determine the calibration factor, and then one to determine the energy of the reaction itself. Has anyone got any questions about that?